Good afternoon, good morning, good evening, ladies and gentlemen, wherever you are in the world. This is Tim Collins, Secretary General of World Stainless, and it is a pleasure to welcome you to our second session of today on Understanding Corrosion, Chapter 2. So for people with good memories, they may recall that back in September of 2020, we had the first part of Understanding Corrosion, which was probably a little more generic than this is going to be today. But before we get into the presentation, if there's somebody on the line who can confirm the sound is okay. We had a small echo first thing this morning. I'm just hoping in the session, the second session today, the sound is good. So if somebody can drop a message in the chat box, that would be much appreciated. A few housekeeping things before we start. We've got confirmation. Thank you, whoever that was, to say the sound is good. Just a few housekeeping things. So first and foremost, everybody attending the webinar will receive a copy of the presentation. So you don't need to ask for that at all. That will happen naturally as you've registered. And the video of the presentation will also be posted to our YouTube channel. So it will be available to re-watch should anybody want to do that. In terms of questions, there will be time at the end for questions, so please pop your questions into the chat function. And if we don't have time to answer all the questions, every question posed will get an email response if it's not responded to today. So please rest assured that you will get a response to any questions. So I hope that clarifies a few things. So without further ado, let's get into the presentation itself. So the first slide up is just our normal disclaimer slide, just to remind people if you want to reuse anything from this presentation, please ask permission from ourselves first. And also just to let people know that the document, the presentation itself is antitrust compliant because we are bound by global antitrust legislation. So in terms of today, there's broadly 6 elements to the presentation. I'll kick off with a short introduction just to set the scene. Then I'll talk about the global impact of corrosion and sort of express that in a couple of different ways. Then we'll consider traditional material choices and perhaps more appropriately what's not quite right with some of those choices. We'll also look at preventing common corrosion types, and we're focusing on 3 different corrosion mechanisms today: galvanic corrosion, pitting corrosion, and what I've termed hidden corrosion. Then we'll have a look at appropriate materials choices, having had that reflection on common corrosion types, and wrap up with a summary before a short Q&A session. So I should be talking for around 45 minutes. Now, let's get going. So, headline impact numbers to start with. The cost of fixing the impact of corrosion is more than 4% of the gross domestic product of the G20 countries. So we're talking big numbers here. And what we often see through our news channels, whether it be television, radio, online, however we access these things, is these big stories where things fail suddenly. They fail before they're expected to. There's often loss of life associated with this, major disruption to urban systems, huge repair costs, and often reputational damage issues. So we see these things fairly regularly all around the world, and we recognize them. However, just if we go back in time before sort of reflecting on corrosion, people started to study corrosion in the 1800s, and Michael Faraday was one of the sort of early sort of people that considered non-corrosive alloys, but he had other scientific priorities, so his interest in corrosion faded away. But then in the early 1900s, a gentleman called Albert Poitevin observed the corrosion benefits of adding chromium additions to steel, which is quite an interesting reflection when you think less than 10 years later, stainless steels actually arrived in Germany, UK, and USA at similar amounts of time. And depending who you talk to, each of those countries will claim they were the first. But I don't think we should argue about that. I think what we should recognize is the benefit of stainless steels. However, I think here is a sort of compelling and maybe discussionable point. So we've had non-corrosive alloys like stainless steels, high nickel alloys around for more than 100 years now. And we see corrosion. It's around us. We see it as we drive to and from our places of work, as we drive around our countries. But I would argue that our corrosion knowledge generally as a society is pretty weak. And this is an interesting starting point to reflect on corrosion from. But also, let's just consider how corrosion is defined. So below the left-hand picture, we have the classic definition of corrosion. It's the deterioration of a material as a result of chemical reactions between the material and the surrounding environment. So that is the classic definition of corrosion. And whilst we will often associate corrosion with metals and the degradation of those metals and alloys, it can affect other materials. So polymers and ceramics are not excluded from corroding. And we should always remember that corrosion in its broadest sense affects most materials. Now let's just reflect moving forward on the global impact of corrosion. Some of this data may be somewhat surprising. So every living thing on Earth is affected to some degree by the impact of corrosion. And the products of corrosion get into everything. They seep into the earth and into aquifers, into rivers, the seas, and even into the air. And you have in this range of the products of corrosion, not just obvious things like rust itself, but chemicals, hazardous materials. And some of these things are really not good for living organisms. And corrosion also causes the following outcomes. We've already touched on a few of these, that buildings and other major structures collapse. We often see collapsed bridges in news channels all the time. When transport systems fail due to corrosion, the consequences are often disastrous because our reliance on transport systems is so great today, and the impact can be loss of life, it can be failure of products getting into supply chains at the right time. There's all sorts of impacts. There's also the failure of energy and utility company assets due to corrosion, which again has big impacts. And then the health and safety dimension we shouldn't ever overlook, because corrosion does hurt and it does kill people, sadly. So in summary, corrosion is A, unsightly, B, it's unnecessarily depleting the world's natural resources. So it's something that we should look to avoid. So let's just reflect further on the global impact. So as we move around, we see corroding and decaying materials every day, and the barrier in the image on this slide is a classic example. But how often do we stop and think about what's happening there and then? And how often do we think about what's going to happen in the future? Have we normalized corrosion so we don't even adjust our heads to the fact that corrosion is all around us? And the interesting thing is the cost of corrosion at a global level is $3 trillion every year. So this is a huge amount of money. And if we applied the best corrosion prevention practices, we could save almost $1 trillion, 900 billion per annum as well. So the benefits of doing the right things are very large indeed. So why do we allow corrosion to occur? I would argue primarily because of three things. One is about knowledge or lack of knowledge. So we don't properly understand corrosion. The second thing is cost pressures. And the third feature is organizational behaviors. This is the way we do our business. This is the way we think about things. And sort of these behaviors get passed down to new recruits. We adopt the same organizational thinking. So we almost become machine-like in our organizational thinking. But let's reflect on the global problem of corrosion from an emissions perspective. And this slide depicts steels. And essentially, you've got two lines here. The blue line is the production emissions associated with global steel production, essentially over the last 40 years. And you can see how that's sort of developed and risen, particularly in the last 20 years. I can't add up because it's 60 years, of course. So if anybody spotted that, but hey ho, schoolboy error along the way. But you see on the black line, the emissions associated with the material replacement that corrosion has driven. And this is about 20% of the total steel production emissions. So what we're doing, and this is only the image of steel products, is we are unnecessarily emitting 20% more than we need to do. And that's significant when you consider that in 2020 we were approaching 4,000 tons per annum. Is that right? No, it's 4 million. I think it's 4 million tons per annum. So we're talking big numbers here, huge numbers. So having set the scene, let's just now reflect on traditional materials choices. So there's no doubt that traditions over many years have delivered what we would class as appropriate or fair outcomes. But we all know that climate change is on us, it's here and now, it's gathering pace, and those traditions need to be reviewed. And much more resilient materials need to be used within our world for a variety of reasons, not just climate change. More people are living in cities. Currently 55% of our population live in urban settings, and that will increase by 2050 to 70%. So we need to use things that are more resilient. But our knowledge along the way has evolved too, so our traditional thinking needs to evolve with it. But in many cases, whilst the knowledge has evolved, it's not in everybody's heads. So currently, our material choices are often dominated and have been dominated for many years by three things, I would argue, namely the cost of materials. And this is a classic case in my head of procurement and operations as two groups of people don't always talk, and only upfront material costs tend to be considered. So the most appropriate materials choice that would be lower cost over the lifetime doesn't always get selected because people are driven by different targets. And ultimately, it comes down to an organizational behavior feature. Secondly, client pressure. Clients often don't fully understand the operating environment and therefore the impact of corrosion. So they put pressure to save money where possible, and that results in suboptimal choices. And thirdly, organizational traditions. I've touched on this, but I've heard so many times people say, well, look, this is the way we do things. It's been successful. Why would we change? And if you doubt that for 1 minute, please go and read an article by a gentleman called Donald Sull of the London School of Economics entitled Why Good Companies Go Bad. And then I think you may well review your thinking. So let's just reflect now on traditional materials choices in a couple of usage areas. So I'd like to start with sort of construction or building an infrastructure. And if we look at typical tons per annum used in this sector, the dominant material is concrete. Then you've got aggregates, brick, and then the bottom of that list of 4 steels. And 1 billion tons is still, but these are big numbers. But you can see the hierarchy of things there. If we reflect on a different usage sector, process plant and associated equipment, then that list, steels top the list generally, although different tons, we're talking millions of tons rather than billions, so just reflect on that. Plastics come next, interestingly, then stainless steels, then aluminium. So you can see the sort of range of materials that are considered. And when you think about those materials and say, well, are all of these materials corrosion resistant? The answer is probably going to be in many cases, no, certainly not the big use materials. So when you consider that, corrosion resistant materials are frequently not the materials of choice in many demanding applications. And why is that? Does that happen? So let's now think about traditional material choices and what's fundamentally wrong with them. So frequently, they are not the optimal choice for corrosion resistance. And that's down firmly to a lack of understanding of the types of corrosion that are likely to occur. And that, in turn, is driven by a lack of understanding of the operating environment. So if you don't have a detailed understanding of the operating environment, not just now, but in the future as well, you will fail to appreciate the types of corrosion. Now, equally, where corrosion resistance is understood, because it's not all everything's in one box and not the other, the solutions are often not good. So I'm going to illustrate that with a couple of solutions. Coatings. Coatings are widely used, and we use them in the home. We paint things regularly in our houses, and that's okay when it's a fashion change. You don't always want to look at the same colour walls, but if you've got a corrosive environment, a coating is ultimately going to fail. They are okay for a short time. So you either have to reapply them or think differently. And many coatings we should recognise are toxic too. So a great example is zinc. Galvanised coatings are popular, and zinc is important for human life in small amounts. But if zinc consistently sort of falls and diffuses into our aquifers and ends up in water systems, what's the long-term impact of high quantities of zinc in our water courses? It's an interesting reflection. I think it's probably too early to tell in the evolution of our society, but it's something we need to be aware of. And then cathodic protection is not suitable in all areas because you do get release of certain ions, zinc and aluminium being quite sort of obvious in this case. So things are there that work, but they're not foolproof. So let's now move on to consider preventing common corrosion types. And I'd like to look at three, as I said: galvanic corrosion, pitting corrosion, and what I've termed hidden corrosion. So we'll start with galvanic corrosion. And this is, I would argue, common yet simple to prevent as a corrosion mechanism. And the illustration here of a swimming pool handrail post shows actually two types of corrosion: galvanic corrosion caused by the inappropriate choice of nuts to fix the stainless bolts and the base plate to the floor itself, and crevice corrosion actually acting underneath the base plate. And crevice corrosion will be dealt with at a different time, but not today. So we're talking about galvanic corrosion. There's two errors here in terms of corrosion prevention on this particular slide. So let's start with galvanic corrosion. So it normally occurs because of, again, three things: lack of material training and knowledge. A classic case of, if you think training is expensive, try ignorance. And the example to the right, it's a similar example. In this case, it's a carbon steel washer holding in place, where you've got a stainless steel bolt and the stainless steel bracket. Another classic error of differing materials. Lack of suitable materials is another reason, and fixings is a great example, as illustrated here. And this comes when there is pressure to finish installations. People put under pressure will use what they've got, not use what is right. So this is another classic case. And then the third thing is subcontracting without detailed briefing. If you want somebody else to act on your behalf, you've got to tell them everything, not just how to do the job, but how to do the job with the right materials. So let's just remind ourselves of what galvanic corrosion is. So it's damage that occurs, or corrosion damage that occurs, when two different metals are in electrical contact, i.e. touching each other, with a conducting electrolyte, generally a liquid or close to liquid product present. And you categorize materials into two groups: noble metals, which are generally protected from corrosion in this case, and less noble metals that tend to corrode. And you've got to have three conditions in place. These metals or alloys must be electrochemically dissimilar. So that's one of the features, and I'll explain that in a moment. They must be in electrical contact, so touching each other, and they must be exposed to the present electrolyte. So they're the three things that will trigger galvanic corrosion. So let's now, just before I move on, so just to clarify, noble metals or cathodic metals resist galvanic corrosion, and less noble metals or anodic metals will preferentially corrode when they're coupled. That's just a reminder there. So here is the hierarchy table with 24 different materials on it. And the items with the lowest numbers are the more noble items. So graphite, gold at the top, and then at the bottom, as you move through, you've got aluminium, zinc, and magnesium. And when you couple these things together, they become an electrical content. You have an electrolyte, can even be water present. You'll get an electric current flowing between them. And the less noble metal, the things towards the bottom of this list will corrode preferentially. So you can see here that if you couple something like a 2205 duplex stainless position 6 with a carbon steel, there is a huge galvanic potential difference. The carbon steel will corrode, using this example. But if you're coupling together things that are very close in this hierarchy table, then you're very unlikely to get corrosion. So the difference between a 2507 duplex stainless steel and a 2205 duplex stainless steel, it's 10 millivolts. You essentially won't get corrosion. Now let's sort of reflect on that with a simple to understand diagram. So here we only have 7 materials, ranging from zinc at the top of this list to stainless steel, a generic stainless steel at the bottom. And now I've color coded it for ease of understanding. So zinc is the least noble metal, stainless is the most noble in this simple 7 material hierarchy. If you couple zinc with zinc, it doesn't corrode, no current flows. If you couple zinc with stainless steel, the zinc will corrode, and it's in the red zone, so it's serious galvanic corrosion. It will corrode fast. So you can see a hierarchy here developing that I've color coded to help try and explain. So essentially you aim for the green zone and avoid the other colors, otherwise you will fall foul of galvanic corrosion. So let's now just reflect simply, having looked at galvanic corrosion, what are the prevention rules? So the first thing is to understand that hierarchy, that galvanic corrosion hierarchy. If you don't have that in your back pocket on your mobile phone and you're working in a corrosive environment, building things, replacing things, you will undoubtedly fall foul if you're not a sort of person with a great memory, shall I say. Don't ever have dissimilar metals in contact if an electrolyte can be present, liquid or semi-liquid. And remember, the electrolyte doesn't have to be present 100% of the time. 10% of the time will trigger galvanic corrosion. So you're not looking to say, hey, this is an environment where it rains now and again. That will still cause you a problem. Never forget that all components you are working with are important. Never try to save time and cost by using any fixings available. And it's usually the fixings where this problem is spotted first. And if you try and take shortcuts with installations, they can have serious future consequences for your organization and for people within those organizations, because you'll become liable for failures. It's not hard to prove that galvanic corrosion has occurred. So quite simple, 4 rules. The top ones are the most important, but remember, please don't take shortcuts. So let's now move on to reflect on pitting corrosion. So pitting corrosion is an extremely localized form of corrosion. It leads to the creation of small holes in the alloy. It's almost like drilling into the alloy itself. Chloride ions are well known to cause pitting corrosion because they destabilize any passive films on the surface, even those of stainless steels. And I'll talk a bit more about that shortly. And the image to the right here is of 6 bolt heads, each one in a different material, that has been immersed in seawater for just 24 hours. And you can see the impact. So at the bottom, the stainless steel and the brass have just started to get some minor rust spotting on the surface, but nothing serious. Whereas at the top, the aluminium and the galvanized steel, you're already starting to see some corrosion products. The black steel, mid left, is looking poor, the bronze looking a little better. So this is a very early indication of what's going to happen if you don't consider pitting corrosion and the impact of chlorides correctly. So let's consider influencing factors. So there's no doubt the temperature of the operating environment has an impact on pitting corrosion. As temperature increases, the likelihood of pitting corrosion increases. And if you want to use appropriate materials to avoid pitting corrosion, stainless steels are generally the better group of materials, but they have to be more highly alloyed, and adding molybdenum really helps. Unsurprisingly, the chloride content of the operating environment has an impact too, and the pitting corrosion resistance decreases as the log of the chloride concentration increases. That's an important relationship to remember. And again, molybdenum in stainless steel gives you the protection that you want. And then the chemical analysis more generally, particularly of stainless steel in this environment, you don't want to use non-stainless steels in an environment loaded with chlorides. The elements that have the most impact is nickel that we've talked about, molybdenum that we've talked about, nitrogen and chromium, I should say, but they all have different impacts. Nitrogen has a massive impact, but the more nitrogen you add, the poorer the hot workability of the product is. Molybdenum has this good impact at 3.3 times its content, and chromium has a one-time positive effect, times 1, I should say. And those two, molybdenum and chromium, don't affect the hot workability of the stainless steel. Now, the way to sort of assess this is through what's known as the pitting resistance equivalent number, which I'll talk about in a moment. But just to dispel any myths, at the bottom of this table, nickel doesn't have an impact on pitting corrosion, and many people I've encountered think it does. Please be rest assured it really doesn't. So now let's look at pitting corrosion resistance as a sort of equation that allows us to choose appropriate grades. And I've put on here 2 threshold levels: the pitting resistance equivalent number for a seawater splash environment, and the pitting resistance equivalent number for a seawater immersion environment. And you'll see one is about 22 and the other is just a shade above 35. And you can see the range of grades with carbon steel in the bottom left, which is pretty rubbish in a seawater environment, to 654 high molybdenum alloy in the top right, and you've got a range of stainless grades in the middle. So even if you're in a seawater splash environment, please never use a 304 grade. You will just suffer disappointment. And equally, if you're going to immerse something into a seawater environment, you shouldn't be choosing a 316 or a very lean duplex grade. These are not the right choices of material. So this gives a guidance. Of course, there's a continuum on here. It's not as exactly precise as this, but this gives you a real helpful introductory guide. But we can't ignore temperature, because I mentioned temperature was important. And this chart shows the different critical pitting temperatures of a selection of materials. So you have carbon steel on the left-hand side, and pitting corrosion of carbon steel will start at temperatures below 0 degrees centigrade. So not even a warm environment. And then you see where the 304L and 316L grades are, still relatively cool. And it's only the higher alloyed grades where you get into much higher temperatures. And I've shown on the far right, nickel alloy 625 as just an indication of the benefit of nickel alloys too. And these temperatures are derived from ASTM test methods, the immersion test methods that are used to sort of create these values. So again, this is a very useful reference table when you're thinking about pitting corrosion and appropriate choice of materials. So to sum up on pitting corrosion, what is the right thinking? First and foremost, you have to understand the operating environment. So the corrosive media that are present, the contact mechanisms, and the likely time to impact. Think hard and carefully about the influence of operating temperatures. Many people fall foul because they don't choose the best grade for the environment because they've not thought about operating temperatures, just chloride concentration. You have to determine the appropriate pitting resistance equivalent number needed for that environment. So once you know what's going on in the environment, get to the right pitting resistance equivalent number, and that allows you to choose the grade. Now, within this presentation pack, I don't have time to go through this today, but there is guidance on how to do this in the presentation appendices. So there, that will guide you through how to make the right choice. And then recognize that the environment may change. The environment today will not be the same environment, particularly in light of climate change, as in 10 years' time. So if you're building for longevity, which we should be, you've got to make some kind of lifetime assessment. It's not always easy to do, but it is an imperative. So let's move on now to look at the third of these categories, hidden corrosion. And this is not a classic corrosion mechanism in itself, but it is a feature because of the way we choose to build things. We hide products that will corrode. And I'm going to specifically illustrate this with reinforced concrete. And the main cause of corrosion within concrete, particularly of the reinforcement, is chloride diffusion. 40% of cases are down to chloride diffusion. And chlorides can penetrate through the concrete by diffusion to reach the reinforcement because of two primary causes. One is the use of chloride containing materials for creating the concrete. So seawater for mixing the concrete, additives containing chlorides, and aggregates containing chlorides. Once you start doing things in that way, you are lining yourself up for a problem. But also the exposure of whatever you create to de-icing salts, seawater, or even chloride containing products that are stored within concrete structures. So you have to recognize it's more than just direct contact, other things can occur. And the permeability of the concrete is a key factor that affects the diffusion rate of the corrosive media, chlorides in this case we're primarily looking at. And modern structures tend to be built with concrete that's specified for low permeability, so slowing down that diffusion rate. So that's beneficial, but it's not perfect. Older structures are less likely to have used low permeability concrete. So older structures will be showing some evidence of corrosion within the concrete, and Autobahn bridges in Germany are a great example of that. Now, when we're thinking about the hidden corrosion of reinforced concrete, there's a few things we need to understand, because people say, hey, when you've got steel reinforcement in concrete and you've got concrete that's primarily alkaline, the steel reinforcement will have a passive layer, and it will. And that's protected by that because of that initial alkalinity of the concrete, a pH level somewhere between 13 to 14. So the steel inside is not going to corrode at that stage. However, there are things that diffuse through the concrete, the chloride ions, CO2 in the air, and even moisture. And these things all have a different purpose when it comes to hidden corrosion. So as the CO2 diffuses through the concrete, carbonation of the concrete occurs. And when that carbonation reaches the steel reinforcement, that passive layer is destroyed. So depassivation occurs. When that occurs, the pH level of the reinforcement falls, and corrosion of the steel initiates when the pH level reaches 9 and continues to fall below 9. So you have a set of mechanisms going off here that all sort of build together to cause a problem. And it should also be noted that SO4 ions, which can be sometimes present in and around concrete structures, diffuse into the concrete but only degrade the concrete. So that causes another problem in itself, that it speeds up the diffusion of other things. So you've got many mechanisms going off here that can all occur at the same time. So to avoid this, what can we do? There are generally 4 areas to think. You can increase the concrete cover. You can make the diffusion take longer. And just increasing the concrete cover by 25 millimeters or an inch increases the diffusion time by a factor of 2. And that appears to be great, simple, easy. But what you have to consider is that's a huge structural weight increase, because all external faces need to have that increased cover. So you get a benefit, but you get a big negative too. You can use coated steel reinforcement, for example, epoxy coated or galvanized, and that provides you with surface protection. It appears to be a benefit with immediate results, and it will be for a period of time. But what we should never forget is coatings fail, both during handling and in service. And the way reinforcement materials are handled means that you will get some level of coating failures during material handling, and that is opening up the opportunities for corrosion. So yes, you'll get some protection, but you'll get some downsides. And when corrosion kicks in and occurs, coatings fail faster. You can decrease the permeability of concrete, slow down that diffusion rate. Great idea. And that will extend the time before corrosion is initiated. But what comes with that is an increasing cost of the concrete and requires precise production techniques. So you have to ensure that the capability of your workforce will allow the benefits you expect to occur. And then you could choose selective use of stainless steel. And I say selective, this is really important, because when you think about diffusion, the time to diffuse into the center of a concrete structure is incredibly long, but the time to diffuse through smaller surface layers to the first level of reinforcement is much shorter. And if you change that to those first levels of reinforcement on duplex stainless steel, you will prevent corrosion in the structure for many, many decades. And that will also reduce the concrete needed by some 20 to 25%, because the high strength duplex stainless steels bring an additional benefit you can exploit. But the downside is you'll increase the reinforcement cost by around 10%. It's not extreme, it's not to be worried about, because the savings you get on maintenance, which I'll illustrate shortly, are huge. So let's try and depict what happens with chloride corrosion of reinforcement. So here we have a concrete piece in the blue box and a piece of rebar contained within that, the black cylinder in the middle. And we've got carbon dioxide, chloride ions and water in the air. And we shouldn't forget, we've got SO4 ions in this case too. But at the start, before any diffusion occurs, we've got robust reinforced concrete in place. Now, we're not particularly going to talk about SO4 ions in this case, but we do recognize they damage the concrete, they degrade the concrete. So the first stage to consider is what happens. So the CO2 moves through the concrete, diffuses through the concrete and causes carbonation of the concrete. And the chloride ions follow that, and water equally from the air. But everything's okay. So we've got carbonated reinforced concrete, but the reinforcement is untouched. But once the carbonation reaches the reinforcement, then the passive layer on that reinforcement is destroyed. And the chloride ions that are progressively diffusing through can start to attack the reinforcement that's in place. So then you get non-passive reinforcement ready to corrode. And then in the fourth picture, the reinforcement, the rusty rebar now has corroded, it's become rusty, and with that you get a volume expansion. So it looks bigger, but it's contained in concrete. So that causes the concrete to crack and spall. And what you then have is a real problem, because corrosion occurs faster. You've now opened up the concrete structure to invite more and more corrosion. So that's the basic mechanism that we see. And there are many variables that influence that, and I've touched on one or two earlier. But what you should never forget is when you've got reinforcement and it's this first line of reinforcement in place, you need to understand whether chloride corrosion is going to happen reasonably quickly or not, and go back to the design stage and think about preventing that. So let's illustrate that now with a case study based on the motorway, the Midland Link motorway viaducts in Birmingham. One part of this is famously known as Spaghetti Junction. And this was 21 kilometres of elevated motorway, and it suffered a sort of checkered history. The design was not good, and the limitations of the design affected the long-term durability of the material, particularly concrete. The concrete slabs on which the running surfaces were based were much thinner than they should have been. Drainage facilities were poor. During construction, many materials were not available, and poor workmanship, because this was needed to be done quickly, was fairly evident throughout. And if anybody's fast with their eyes, they'll spot a small smelling mistake in this slide, which I will correct before it comes out to everybody. So in this case, the original bridge joints failed within 5 years of opening. So that's really fast. And significant corrosion and degradation due to chloride ingress was noted. The concrete cracked and spalls, as I've illustrated one of the previous slides, and this was exacerbated by the sort of high intensity of heavy goods vehicles using it, causing sort of wear and vibration into the materials. These structures were equally not designed for ease of maintenance. Another important lesson here. Now let's look at one of those viaducts. So this is the life cycle costs over 17 years. And the deep red line here is reality. This is what actually happened. And the blue line is, you know, if they thought about partial use of stainless, what would have happened? So this dates back to 1972. So we're talking a long time ago. And the cost to build this, this single viaduct in this case, this is part of the overall system, was a little under 30 million euros. And you can see in year 4 after opening, already maintenance costs were being incurred. And over the 17 years of which this is projected, the maintenance costs were almost 2 times the original build cost. That's frightening. Whereas if 10% stainless reinforcement had been used, it would have added initially 11% to the build cost, but there would have been replacement and repair costs of partial areas of this, no doubt, but it wouldn't have increased anywhere near as much. So the difference is more than 40 million euros over 17 years. And in the early 1990s, they switched to cathodic protection, but only after these frightening costs had been sort of taken on board and sort of had a negative impact on the whole system. So this is a great example of how to get it wrong and how the impact of getting it wrong is quite quick. Now let's just also reflect on marine environments. So this is a corrosion timeline development for a marine system. There's lots of lines here, so I'll explain this in stages. So you've got, as a y-axis here, an extent of deterioration of materials in the concrete structure. And the reinforcement choices here are carbon steel, the black line, 2304 duplex stainless, the green line, and you've got 2 other coloured lines, and this represents, these are the lines that represent the economic life range of the structure. So when your corrosion enters that zone, you have a real question to ask. Well, what you see looking at the carbon steel choice, which is a traditional, more traditional material choice, you get corrosion initiation after about 15 years, but the acceleration of corrosion is rapid. And then you get a step down, and that's because some level of repairs have been carried out after about 20 years, and again after about 40 years. And repairing events temporarily reduce the deterioration. So you get some relief, but not total relief. But you ultimately get to a point where you say, hey, I can't keep throwing money at this. I have to choose what to do next, and replacement is often the decision. But you're looking at somewhere between a 50 and 55-year term. This is not good for a major structure, particularly in a marine environment. You want really to think much longer term. But going back to this notion of selective use of stainless, if you change your reinforcement, so 10 to 15% is stainless, these outer layers of reinforcement, you will extend the life massively. Your cost increase is minimal, and the extent of deterioration is also minimal. So it's not about wholesale changes, it's about selective uses of corrosion resistant materials. So let's sum up hidden corrosion. You have to understand the operating environment, it's absolute imperative. You have to equally understand how the corrosive media present will behave. You can't say, hey, I didn't know about this. This is no excuse. And saving marginal costs is really no excuse. It's really just bad practice, I would argue. And material selection becomes blindingly obvious when you have the facts. If you don't have the facts, it's difficult, I accept that. But having the facts makes it easy. The philosophy to avoid hidden corrosion should always be choose the resilient fit and forget materials and not what I class as install and repair materials. You either choose an easy life or a life of pain, and I know what I'd go for. The small extra cost of resilient materials brings massive other savings. So we should always think in this sort of context. So I'd now, as we're getting towards the end of this, just like to touch on appropriate materials selection. And this is a great sort of image that I've used before in other webinars. This is the Progreso piers in Mexico. On the right, you have the old pier built in 1939, which in a forward-thinking manner used stainless steel reinforcement, still intact today, still looks marvelous. And then you have 30 years later, the smaller pier built in 1969 using carbon steel reinforcement, and it's pretty much disappeared. And that's the benefits of corrosion for you. Choose the right materials, you've got longevity. Choose the wrong materials, you've just got a relic. So thinking about appropriate material selection, we know that materials do degrade over time, and corrosion speeds up that rate of degradation. So if you analyze your operating environment, that will guide your material selection, both now and for the future. An appropriate material selection does not mean expensive materials. Yes, there will probably be some slightly higher upfront costs, but all the benefits come thereafter. So let's think about this using a classic Boston box. So on the bottom side here, I've got initial material costs ranging from low to high. On the left-hand side, I've got the thinking term, short-term thinking at the bottom, long-term thinking up the side. And let's start with traditional materials thinking. This is where sustainability is not prioritized. The operating environment is not fully appreciated, maybe partially appreciated. Asset costs influence material choices, and you have an ongoing maintenance legacy. Ultimately, bad set of outcomes, particularly with things like climate change. If we move to the right of that, this is what I call the folly group of things. This is spending that's not properly thought through. Somebody's got a pot of money left, they want to use it. So you end up with something that I would class as style without substance or stuff without purpose. Not a good area to be in. You've wasted a lot of money for not much benefit. Above that, you have the over-engineering product. So you'll develop something that is good for the long term, but it's significantly over-engineered. It's not the best use of cash when cash is tight. And frequently these things are built in such a way they're not easily expandable in the future. And then you have what I call the sort of more sustainable thinking box. This is low cost, not as low as the traditional material solutions, but still relatively low. And this is novel material choices or solutions involving what I term symbiotic material choices, things that work well together. The operating environment is fully understood. Selective use of resilient materials is allowed. The costs are therefore managed, but it's all about life cycle thinking. Here on this next slide is just a list of specifications where stainless steels are well sort of documented and easy to use. More and more specifications are coming online that will make it easier to work with stainless steels, but there are a fair, and this is only a selection, a fair range of specifications around now that people can call on for guidance and examples. So I'd now like to sort of sum up before we go to Q&A. So in terms of summary, a number of messages here. Corrosion does not have to be inevitable. And furthermore, understanding corrosion is not overly complicated. For the most common corrosion types, there are one or two corrosion types that demand a bit more understanding, but for the common things that we generally see around us, it's not that difficult. Preventing corrosion to extend asset service lives is not costly. It just takes a little more thinking, a little more understanding, and you can save a huge amount of money. If it was our own money, would we think in the way perhaps people have thought in the past? And if you choose not to prevent corrosion, then you must be very wealthy, I would argue, or you can afford to keep funding something for a long time. So the corollary of sort of thinking about corrosion is think about not preventing it and what it's going to cost. And remember, in the summary, stainless steels were invented 110 years ago. They are designed to resist corrosion, but they have many other attributes, whether it's high strength, being formable, weldable, good toughness, even at low temperatures. These products are your friend, and use them wisely and use them effectively. There are more than 200 different stainless steels available today. It's a horses for courses family of materials. If you want something that has high strength and good corrosion resistance, we have things out there for you. And ultimately, when you use stainless steels, they will save you costs. because they reduce the quantity of co-materials that you need in specific projects and installations. They limit or even avoid maintenance. So choosing the right stainless steel will deliver that fit and forget solution that everybody seeks without going mad with your money. So at that point, I'd like to draw things to a close, thank everybody for their attention and say, hey, have we got any questions?
Haven't any questions come in yet, Tim? So we'll see if there's any.
Okay, I hope people found that sort of interesting and enlightening and maybe a little controversial in parts. If people want to ask further questions, you can send inquiries directly to me, collins@worldstainless.org, and we're happy to sort of answer any questions. As I said, this presentation will be circulated to everybody. It'll be posted on YouTube, and we'll be having our next webinar will be in September, where we will focus in a more detailed fashion on stainless steel reinforcement.
Well, you seem to have been crystal clear, Tim. There's no questions whatsoever, or maybe they're still pondering over what they have to ask. Or
yeah, that's no problem. Sometimes no questions is good, but we're always happy to answer questions. So thank you everybody for your attention, for your time, and we look forward to welcoming you to another. Oh, well, we've got something coming in.
How about alternative reinforcement methods to prevent hidden corrosion in concrete? Fiber reinforced polymers exist now that can be used to strengthen concrete structures.
They can. That's a really good point. I didn't talk about fiber reinforced polymers, but they do exist. They're incredibly strong. They're lightweight in turn. The big problem with them is recycling. When you think about stainless steel, 95% of stainless steels are recycled at end of life, captured and recycled. Reinforced polymers, that's a real headache. How do you do that effectively, efficiently, and without huge CO2 emissions? So great product, but they don't support the circular economy so well at the moment. I'm sure things will change, but that's where we're at the minute.
Okay, we have another question.
Okay.
What are the main causes of selective corrosion?
Selective corrosion.
Selective corrosion, like the same material in the same environment. Some areas starts to corrode while others do not. How does it come that it's only a certain area that you have the corrosion?
I mean, corrosion depends on a number of things. I mean, I didn't cover uniform corrosion in this webinar because that's a much easier form of corrosion to understand. But if we think about the three forms that, or the three corrosion types I touched on, galvanic corrosion normally occurs where you've got these sort of dissimilar metals in contact. And without a doubt, the most common sort of examples of galvanic corrosion is incorrect use of fixing materials, without a doubt. So it's the fixings themselves that corrode, or materials around the fixings that corrode, depending on what choice of materials have been used. So it's always an area to pay attention to. When you consider pitting corrosion, now pitting corrosion can be quite varied and selective depending on the environment you're in. So if you're in a seawater splash zone where you don't need such a highly alloyed stainless steel and it rains quite regularly, then pitting corrosion would be very slow to occur because the rainwater will wash the corrosive media off the surfaces. And that's something to be aware of, this sort of weather systems in the environment you're working with. So you might think you could have a problem, but be very mindful of weather systems as well. Whereas when you're in sort of immersion areas for seawater, then you have to think about pitting corrosion occurring both up to the normal water line and at high tide areas as well, and they'll occur at different rates. So you'll get faster corrosion just below the water line than you would above the waterline. As you go deeper, if there's less oxygen present, the corrosion rate will slow down. So you'll get different effects depending on the impact of the seawater and oxygenation around the area. When you think about hidden corrosion, then there's many issues to consider. So if you've got the deck of a bridge in a sort of snow zone above the snow line, or we're using de-icing salts regularly, it's that deck that is going to most likely to suffer the corrosion first, certainly the reinforcement. So you need to focus on that and think about how you use non-corrosive products as reinforcement in the deck area. And a great example is this bridge on the slide now, the Samuel de Champlain Bridge. This was built with 15,000 tons of stainless steel reinforcing bar to last for a long time. And much of that reinforcing bar is in the deck because it's heavily subject to de-icing. So that's not to say there isn't reinforcing bar in the piers as well below that, but the bulk of it goes into the deck. And this design requirement was for more than 125 years in service. The previous bridge, which it replaced, only lasted for 52 years and incurred huge annual maintenance costs just to keep it open in the last decade or so. So I hope that answers the question.
Yeah, I hope so too. Otherwise, they can always come back to us saying, you know, I didn't quite get that. Yeah. Next question, if I may, can you briefly describe the general chemical mechanism that is the underlying cause for corrosion? What happens on the material level?
So on a material level, essentially, you're taking the metal or alloy and oxidizing it. So the interesting thing, let's just deal with steel, which is primarily iron. So when steel corrodes, the pure iron changes to iron oxide. And the interesting thing about this is the oxide layer that we call rust, we're all familiar with it. The molecular structure is much different to the molecular structure in size terms of the iron molecules below it. So that means they don't bond. And people will know if you brush the surface of a rusty steel thing, the rust comes off quite easily. So what effectively happens is these layers just peel away time after time because there is no molecular bonding between the iron, the substrate material, and the oxide of that. Now, stainless steel, by contrast, contains what's called a passive layer. It naturally forms in the presence of oxygen a chromium oxide layer. And that oxide layer is virtually the same molecular size as the iron and the chromium in the substrate stainless steel beneath it. So they bond. They are a tightly bonded material. That layer is invisible, it doesn't come off. So that's why stainless steel remains stainless, and that's why iron or carbon steel rusts. These differences in molecular size are the real difference. And when you have a passive layer, it's self-repairing. You don't need to reapply it. You get lots of benefits. It's just invisible. You don't see it. And this tightly adhering benefit gives you the corrosion resistance for a long, long time, unless, as I've described, you've got things like chloride ions that can attack it. And then they disrupt that passive layer, they cause it to break. But if you add molybdenum, as I explained in the pitting corrosion section, you prevent the passive layer being destroyed. Molybdenum restabilizes the passive layer. So there are always things you can do based on the environment to make the passive layer materials really tough to corrode. I hope that answers the question.
Okay, there's more coming.
Yeah.
What is the best source of information for selecting appropriate stainless steel materials for use in chlorinated potable water applications, so tanks and pipes, for chlorine levels less than 2 ppm?
Okay. Well, the appendices to this presentation will give some guidance there because they contain some relevant information. But I think also understanding the typical chloride level that you're working with, we can give some specific guidance. So I'm not sure who's pitched the question, but if they want to say, hey, I'm dealing with potable water with these levels of chloride content, we can give some clear guidance back. But it have to be on that sort of exchange basis, that some relevant data is supplied to us with the question, and then we'll come back and give advice.
So basically contact us and we'll help you.
Yeah, but we need to know the chemistry of the water.
Okay. And then a question that maybe is a bit of a follow-up on the question from before. Is stainless steel resistant to all various kinds of corrosion, to any cause?
Really good question. I like questions like this, because stainless steel will corrode, depending on the operating environment and the chemical analysis of the stainless steel. So the fact that we have about 200 different stainless steels means they've been designed for different environments that are corrosive. And so some leaner analysis stainless steels, I mean, all stainless steels have to have a minimum of 10.5% chromium to be stainless anyway. But you can add more chromium, nickel, molybdenum, and other elements where necessary to increase the corrosion resistance. So there are two important messages. One, if you understand the operating environment but choose the wrong stainless steel, it will corrode. So that's something you have to avoid. And the clue is in the term, it's stainless, not stain proof. So choosing the right stainless steel is really important. But then the aggressive nature of the environment in very sort of difficult circumstances may even mean that stainless steels are not suitable. So this is where you move into other highly corrosion resistant alloys like nickel alloys. So there are limitations for stainless steel. There aren't many, but yes, there are limitations. So important things is understand your environment, be able to sort of describe your environment with detail. That allows you to choose the right stainless steel, but recognize that stainless steels in certain sort of difficult environments may not be the right choice. We would never suggest to use a stainless steel in an environment for which it's not suited. That's no help to anybody.
Okay. The flow seems to have come to an end. No, it hasn't. No, it's just a thank you.
Okay, that's nice. Whoever said that, thank you very much. We appreciate people's interest and support.
So if the flow has come to an end, I guess we could end the webinar.
You can.
And they can contact us, I guess, with more questions.
Yeah. Anyway, we're happy to deal with questions and enquiries, and we're always happy to support people.
Definitely.
So thank you very much, everybody. Take care. Hope to see you at a future webinar, and always remember, think stainless.